This is the second in a series of resources on integral calculus. We define the idea of an integral. We investigate the fundamental theorem of calculus and look at some basic rules for integrals. We explain the difference between definite and indefinite integrals, looking at a basic example. We consider using Riemann sums as a method for approximating a definite integral. We investigate the integrals for specific function forms, including polynomials and trigonometric functions. We will also look at substitution methods to simplify certain integrals. The previous resource in this series on integrals defined integral as the antiderivative for a function. We also saw that the integral from a to b of a function was equivalent to finding the area from the graph of the function to the x-axis between the x values a and b. How do we combine these two definitions? Suppose we have some function capital F of x, where the derivative of this function with respect to x is the function lowercase f of x. Then the fundamental theorem of calculus states that the integral of lowercase f of x from a to b is equal to capital F of b minus capital F of a. So to find the area between the graph of lowercase f of x and the x-axis, we must find the antiderivative function capital F, evaluate that function at the limits of integration, and subtract those function values. The actual mechanics of this process will be explored in future resources, as will numerous examples. However, the fundamental theorem does lead to some formulas that make the process easier. The integral from a to b of the function f of x is equal to the opposite, or negative, of the integral of the function from b to a of the function f of x. Because the derivative can be thought of as the area from the function graph to the x-axis, it is possible to have a negative area if the function graph is below the x-axis. So this first formula helps to ensure that the area stays positive. Another useful formula for integrals is that the integral of a constant multiplied by a function is equal to the constant multiplied by the integral. Sometimes it is also helpful to break a region of integration into sections. This proves useful when a function has regions that are above and below the x-axis, as it can be combined with the first formula to find a total absolute area. One final formula for simplifying integrals is that if we have the integral of a sum or difference of two functions, this is equal to the sum or difference of the integrals of the individual functions. In future resources, we will use these basic formulas to simplify, or even determine, the integrals of various function forms and examples.